Hello, my name is Tyler Chen from the Newton Frontier. On this week's episode of Math Proof Monday, we will be discussing two alternative methods to solve a simple falling ball problem in physics using Newton's second law and Lagrangian mechanics. Suppose we dropped a 2 kilogram ball from a height of 10 meters without any resistance. What would the force of gravity be on the ball? We can evaluate this scenario using the equation force equals mass times acceleration. Given that acceleration equals g, or negative 9.81 meters per second squared, and the force of gravity is the only force acting upon the ball, we can plug in our values to find that the force of gravity acting on the ball is equal to negative 19.62 newtons. But why? Newton's second law states that force is proportional to the change in momentum per change in time. This can be written mathematically as F net is proportional to delta P over delta T. If we plug in the equation for change in momentum, we can see that force is proportional to the mass times change in velocity over time. This can be written as force is proportional to mass times acceleration. If we use proportionality constant of k equals 1, we can get the famous equation force equals mass times acceleration, which we previously used to find the force of gravity on the falling ball. But what if we use a different method to solve this problem? Let's take a look through the lens of Lagrangian mechanics. Let's recall the falling ball. How can we find the force of gravity on the ball now? The Lagrangian for an object can be given by the kinetic energy minus the potential energy of the object. This is more commonly written as T minus V. In this case, T, the kinetic energy, is equal to 1/2 mass times velocity squared. 1 dot over y just means velocity, and 2 dots over y means acceleration, while V is equal to the gravitational potential energy of the ball, just mgy. The Euler-Lagrange equation in this situation can be given as the derivative of time times the partial of the Lagrangian with respect to velocity minus the partial of the Lagrangian with respect to position. This is equal to 0. The partial of the Lagrangian with respect to position is equal to 0 minus mg, while the derivative of time times the partial of the Lagrangian with respect to velocity is equal to mass times acceleration. This means that mass times acceleration plus mg equals 0. Mass times acceleration? Wait, that looks familiar. Mass times acceleration is just force. And if we rearrange the equation, we can find that the force of gravity on the ball is the same as what we got using Newton's second law, negative 19.62 newtons. The sign is originally incorrect because Lagrangians are an energy, a scalar property. So what? Why did I just use an extremely overcomplicated method to prove something we already knew using Newton's second law? Why would someone use Lagrangian mechanics at all when they can use Newtonian mechanics? Do I enjoy making my viewers suffer by making them watch me perform useless mathematical calculations? We often look at physics as explicit answers to how reality works. It is easy to find comfort in the belief that we have definitive answers to our fundamental questions. However, the truth is that our answers to these questions are not set in stone. Physical laws such as those laid out by Newton have been rigorously tested and proven countless times. However, if we were able to prove them wrong just once, they would no longer be law. In fact, this has been done before. It has been proven that Newton's laws don't function properly on the atomic and subatomic scale. This brings us to the point of the lesson. The reason for unnecessarily using Lagrangian mechanics on top of Newton's second law is to show the reality of physics. The physical theories that we hold are not certainties of the universe, but rather models that are able to accurately describe the natural phenomena present. And in some cases, certain models are worse or better, if not entirely incorrect to use, than others. In our example, it was not incorrect to use Lagrangian mechanics, but rather unnecessary. However, if we were to solve a problem with multiple pendulums connected by springs with varying initial velocities, it would be much more effective to use Lagrangian mechanics. Furthermore, if we were to try and solve a quantum field theory problem in a Newtonian fashion, our answer would likely be entirely incorrect. So remember, our physical theories are models of the universe, not laws as we so often describe them.